Hola chicos y chicas, soy Nicolás y vamos a hacer el sexto video de cálculo y hoy vamos a hacer la regla de powers. No, I'm not going to do it all in Spanish. So in the in the last video, I did the definition of the derivative and I took some basic derivatives using that definition. And these were the three that I took derivatives of. The derivative of x squared turned out to be 2x. The derivative of 2x turned out to be 2. And the derivative of 2 or any constant turned out to be 0. Now, I wrote them a little weird on purpose to hopefully notice a pattern. The pattern is that if I have d over dx of x to the n, what that turns into is n times x to the n minus 1. And you'll notice that this is true for the x squared and for the 2x. In other words, the exponent, you can imagine it hopping down in front as a coefficient and then it leaves one less than it. That's how a lot of people like to think about it. I really don't think about it like that, but if it helps you, go for it. So let me try to give some reason for why this might be. If we were to plug this into the limit definition of the derivative, we get the limit as h goes to 0 of x plus h to the n minus x to the n over h, which really the only hard part is expanding this with multinomial theorem, or binomial theorem, not multinomial theorem. So we get x to the n plus, now we would have a n choose 1, which is just n. I'll write it though as n choose 1. n choose 1, x to the n minus 1 h, plus, I don't really have to write that many more. N choose 2 x to the n minus 2 h squared. I'm running out of room too. Hopefully that got it all. Okay, cool. Okay, plus dot dot dot. And in the end, we would just have an h to the n. And that's all going to be over h. So, and minus the x to the n from here. Okay, so the x to the n's, they cancel out. And then every term here has a factor of h in it, which is very nice because then we can cancel out the denominator. So we will get the limit as h goes to 0 of h times, and I'll just write it as n, because n choose 1 is n, nx to the n minus 1 plus h times n choose 2, and I don't need to calculate that. You'll see why in a second, times x to the n minus 2 plus yada 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 plus h to the n minus 1 all over h. Cancel out the h's, and now as h goes to 0, every term after this nx to the n minus 1 also goes to 0 because every other term has a factor of h in it. So this term, all these terms go away, and we're just left with the nx to the n minus 1. And this is why the derivative of x to the n is nx to the n minus 1. Now, let's establish some more derivatives here. For example, probably the next common thing I would want to do would probably be the derivative of the trig function. So for example, what's the derivative with respect to x of the sine of x? Well, that's the limit as h goes to 0 of sine of x plus h minus the sine of x over h, which using some trig is the limit as h goes to 0 of sine x cosine of h, not to be confused with hyperbolic cosine. That was just a joke. Plus cosine x times the sine of h, not to be confused with the hyperbolic sine. Sorry, I shouldn't be messing with you like that. Okay, all over h. Oh, whoopsies. I forgot the minus sine x at the end. Okay. Good thing I caught that, because that would have messed me up later. Minus sine of x. Okay. Now, how do I want to write this? I think I want to write it like this. The limit as h goes to 0 of sine of x times cosine of h minus 1 over h plus cosine of x times sine of h over h. Yep. Now, as we take the limit as h goes to 0, well, with respect to h, x is held as a constant, so these two really just stay as they are, and we're just going to focus on these here. If you watched my last videos, you will know that the limit as h goes to 0 of the sine of h over h is just 1, and the limit as h goes to 0 of the cosine of h minus 1 is 0. So what this just turns into, this whole term goes away, and we just get cosine of x. So the derivative of the sine of x is the cosine of x. Let's do, I am thinking I'm going to let you do it because it really is very much the same. You should find that the derivative of the cosine of x, using the limit definition, will give you the negative of the sine of x, and then the derivative of the, with respect to x, of the negative of the sine of x would just be the negative of the cosine of x, because the derivative of sine is cosine, so you can just stick in negatives there. And then the derivative with respect to x of negative cosine of x is just sine of x, because that's just coming from this here, and we're just sticking in a negative on both sides. So the sines and cosines, they repeat really in periods of 4, right? You start with sine x, differentiate, you get cosine x, differentiate, you get negative sine x, differentiate, you get negative cosine x, and then you're back where you started. Okay. Now let's see if I can remember how to do this one. We'll do the derivative with respect to x of the tangent of x. No, I'm not going to be able to do that one now. What I'm instead going to do is introduce 3 more rules that we can follow here to differentiate. And these 3 main rules, they come up quite a lot. They're the product rule, the quotient rule, which is really, the quotient rule is a pain, and you don't use it all that much, and it's actually just a special case of the product rule. So really just the product quotient and the chain rule. Chain rule is used so much. Very, very common rule to use. So let's start out with the product rule. What does it say? It says that if we're taking the derivative of the product of 2 functions, then let's say we have the derivative of f of x times g of x, then that's just going to be f of x times the derivative of g of x plus g of x times the derivative of f of x. So basically the product rule is saying, all right, what we can do is if we've got the product of 2 functions, we can keep the first one the same, differentiate the second, and then keep the second one the same, and then differentiate the first. If we had 3 functions in terms of x, say, I'm not going to write the f of x, I'm just going to write f, then just know that they're functions of x. If I had f, g, and h, and I want to take the derivative of all that, then it's a similar pattern. It's f, g times h, the derivative of h, plus f times the derivative of g times just the normal h, plus the derivative of f times just the normal g and h. So basically, the product rule is summing up as many, it's got n sums if you've got n functions that are all being multiplied together, and you just take the derivative of each one separately within the sum. Okay, now I would like to do a proof of the product rule, and so let's do that. If I have h of x being the product of two functions f of x and g of x, what I can do is take the limit definition of the derivative. This is, and since I'm using h, you'll see this is the other way they'll write it. They'll write the limit as delta x goes to 0 instead of h. It's the same thing. In other words, as the secant line, the distance between the 2 points that make up the secant line coincide with each other. So that's what the delta x, that's what we're referring to. So the limit as delta x goes to 0 of h of x plus delta x minus h of x all over delta x. That's our limit definition of the derivative, which we could write as the limit as delta x goes to 0 of f of x plus delta x times g of x plus delta x minus f of x g of x all over delta x. Okay, now here's a little bit of the tricky part. I'm gonna add 0. I'm gonna add 0 in a convenient form. It is funny to me that the most basic rules in calculus that are used so much are ultimately proved by adding nothing. Anyway, so we have f of x plus delta x times g of x plus delta x. Now, what I'm going to do is I'm going to add 0, and my 0 is going to be in the form negative f of x g of x plus delta x plus f of x times g of x plus delta x. Okay, and then we still have the minus f of x g of x, and all of this schmozkin is over delta x. So now here was why I added that particular 0. So I added it because now I can write this as the limit as delta x goes to 0 of g of x plus delta x times f of x plus delta x minus f of x over delta x. Okay. Plus, now, so I grouped, what did I group? I grouped the first two, right? Group this term and this term. Okay, plus now, f of x times g of x plus delta x minus g of x, and that's all divided by delta x. And we're taking the limit of all of this, so this should all be in parentheses as well. Now, watch this. Okay, so if we have, let's first focus on this first term here in the sum, this term here. if we have the limit of a product, right, this g of x times delta x times all of this stuff, we can make that the product of the limits. So if I take the limit as delta x goes to 0 of g of x plus delta x, well, that's just g of x, because delta x becomes 0. And now the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, that's the limit definition of the derivative. That's the limit definition of f of x, of its derivative. So all of this just becomes f prime of x. Now, plus f of x, because with respect to x, or with respect to delta x, the normal x is just a constant. And now all of this is the limit definition of the derivative of g of x. So this is just g prime of x. And so with that, we're done. And by the way, I have to say here, for those of you who don't know what QED means at the end of every math proof, it's Latin quod erat demonstratum, or if you don't know Latin and you want to maybe kind of rub your proof in somebody else's face, you say, well, it stands for quite easily done. Also, sometimes you'll add a w to the fifth, which was what we wanted. Anyway, okay, so why did I add that particular 0? I added that 0 because it because it worked. I mean, okay, so I knew that if I wanted to fit the form of the limit definition of the derivative, because I knew I would be getting derivatives in my product rule. And so I said, well, in this here, this f of x plus delta x, if I were to take the limit definition of the derivative of f, I need a delta x, which I have here. I have an f of x plus delta x. All I need to do is subtract an f of x, okay? And since this g of x is attached here, I need to also multiply my f of x by this g of x plus delta x so that I can then factor it out here. And then since I subtracted this part, I need to then add that same part here because I can only add 0 or multiply by 1. So that's some motivation, I guess, as to how I got that answer. The thing is, though, is that really it ultimately is circular reasoning, what I just said, because I was trying to fit this form here, which means I would have already known the product rule and then would be adding 0 so that I could fit the form. So it's kind of circular. I mean, really, what happened is some guy was sitting down thinking about derivatives, and he said, well, I can add this form of 0, and he was probably a lot more brilliant than I would ever be, and he ended up proving the product rule. And there are other ways to go about proving the product rule. But this is the easiest way, truthfully. Now, the quotient rule is what I am actually. I'm gonna do the chain rule next. The chain rule. So the chain rule is probably the most important rule for differentiation in calculus. So the chain rule says that if I've got a function f and I'm composing another function g inside of it, so f of g of x, if I'm taking the derivative of f of g of x, what it says is that if I take the derivative with respect to x of f of g of x, I get f prime of g of x times g prime of x. So you could think of this as the derivative of the outer function times the derivative of the inner function. That helps some people. So as an example, oh, actually, I kind of want to do the proof first, and then we'll do the example. So how do I want to start? I think I'm going to use the limit definition of the derivative. So maybe let's see what happens. Limit as h goes to 0 of f of g. I think I'm actually going to use the alternate definition of the derivative as well. The alternate definition of the derivative is that f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. And hopefully you see that this is saying the exact same thing as the first definition of the derivative. You're still just basically taking the slope formula and letting the 2 points at x and at a come together. And so then the secant line that goes through those 2 points as the 2 points come together will approach the tangent line. And so it's the same definition. It's the same definition of the derivative. Now, I think I want to use this definition of the derivative. So what I can do is I can write this as the limit as x approaches a of f of g of x minus f of g of a over x minus a. Okay. Now, I think now what I want to do I think I want to multiply by 1. F of, see, I want to fit the form of this here. So what I really want what if I multiplied by g of x minus g of a over g of x minus g of a? Then I would get the limit as x goes to a yeah, that's it. Okay. Yeah. Okay, so I would have the limit as x goes to a of f of g of x minus f of g of a over, and now what I'm going to write this denominator over g of x minus g of a, and then I'm going to multiply that by g of x minus g of a over x minus a. That's it. And so now this is the limit definition of f prime of g of x, and then this is the limit definition of g prime of x, and that right there is the chain rule for two functions. And now the last rule that I would like to prove is the quotient rule. And so the quotient rule is, if I have the product in the chain rule, the quotient rule directly follows. So let's say I'm taking the derivative with respect to x of f of x over g of x, in other words, the quotient of two functions. Then I can make this the derivative with respect to x of f of x times g of x to the negative 1, which is using the product rule. That's, okay, we keep f and we then differentiate g of x. So we differentiate g of x, we first have to use the power rule. So we get a times a negative g of x to the negative 2 But now we also have to use the chain rule because we have to take the derivative of this inside function, which is g of x. And so we get a g prime of x. Now we add the derivative of f of x, and then we keep the g of x to the -1. Okay, so I can write this now as I think what I'll do is I'll write it as f prime of x times g of x times g of x to the -2, because g of x times g of x to the -2 is g of x to the -1, minus f of x g prime of x times g of x to the -2. And now I can factor out a g of x to the -2, and I can get, I'll write it as g of x f prime of x minus f of x g prime of x over g of x squared. And that is the quotient rule. There's the chain rule and then the product rule. And so you can see that the chain or the quotient rule is pretty ugly, and I try to stay away from it as much as I can. Product rule and quotient